Hello everyone, welcome back to our lectures. Today we will be talking about Introduction to Carbohydrate and Stereochemistry. Once again, Meku Denzo is speaking. Let us immediately take it off. I have a beautiful quote here from someone very popular indeed, even in the United States, Professor Wole Soyinka. Professor Wole Soyinka is a Nigerian playwright, poet, and essayist. He was awarded the Nobel Prize in Literature in 1986, and in fact, he became the first sub-Saharan African to be so honored in that category. He has something to tell us. Let's listen. He says, "No one is rich enough to buy yesterday, but if you hustle hard, tomorrow could be yours." Again, no one is rich enough to buy yesterday, but if you hustle hard, tomorrow is yours. This is a food for thought. The yesterday is gone, the past is in the past, but the future is coming. And if we lay the proper foundation, we're going to reap the fruits of the future. That is exactly the food for thought from Professor Wole Soyinka. Let's immediately take it off from there. Now, the following learning objectives are what we're going to be covering in this lecture. Number one, we're going to describe the functions of carbohydrate. We'll classify carbohydrate as monosaccharide, disaccharide, and polysaccharide. And then, thirdly, we recognize and identify monosaccharide or other compounds that have the chiral carbon atoms. We understand what the chirality means. And then from there, we now use Fischer projections to represent the D and L compounds, particularly as that relates to carbohydrate. That's what we're going to see this as we move on. So the first thing we need to do, remember, the GOB series is divided into two parts. The first part is the inorganic chemistry and physical chemistry. The second part is the biochemistry part, the organic and biochemistry part. So introduction to this particular class, or rather carbohydrate, will be the first part of biochemistry we're going to be talking about. So but before we do that, let's define biochemistry. So biochemistry is the study of chemical and physiochemical processes and compounds in living organisms. You see, living organisms also have their own chemical properties, their own physical properties. So those particular reactions, studying those compounds in these living organisms and those reactions to undergo is the subject area of biochemistry. And in fact, biochemistry can be properly seen as just the molecular logic of life. The molecular logic of life. And then what about those compounds that we see in living organisms have a unique name? The unique name are the biomolecules. Those compounds that are seen in the living organisms are called biomolecules. So biomolecules are a general term to describe organic compounds found in living organisms. And what do? They perform important functions to maintain life. They perform various functions to make sure that life exists. And they include the following: the carbohydrates, like we're going to be seeing in this class, carbohydrates, the proteins, lipids, the nucleic acid, of course, informational molecules, the vitamins, which act as coenzymes, which then help the enzymes to function, the enzymes themselves, and even the coenzyme that help the enzyme to function. So these are a couple of the biomolecules that we're going to be looking at in this class. Because this class is the GOB series, we may not fully go into those particular details, but the background we're going to be laying on this is going to help you as you move on with your various careers. Then what are carbohydrates? Let's just start. Now, carbohydrate remains our subject of the matter in this class. So carbohydrates are defined as polyhydroxy, aldehyde, or ketone, or substances that will produce or yield such compounds on hydrolysis. So look at the word poly. Hydroxy means there are so many hydroxyl groups. Poly means so many hydroxyl groups, so many OH groups. Then those OH groups, those compounds will have an OH group, and they will either be aldehyde or ketone. So those are the two important functional groups we'll be talking about here. We'll be talking about the OH group, we'll be talking about the ketone. We're going to be talking about the ketone. We'll be talking about that's not ketone, the aldehyde, and then the ketones. And then all those substances, when you break them down, they can also release such products that have hydroxy group, aldehyde, or ketone. So common examples is the glucose we see every day, starch, which is the most common staple we have around, the ribose, cellulose, which you find in plant, the maltose, also which is the disaccharide, and chitin. Chitin forms the exoskeleton of insects and crustaceans. So we now go and begin to take this thing one by one. Now, this picture here, I have a lot of pictures, beautiful pictures here. Like most of these pictures, I put the sources. These two pictures, I got them from public domain. Public domain pictures is a free online repository of pictures. And this, I got it from Shutterstock. You can see the watermark is there. Now, so these are the common sources of carbohydrates. So carbohydrate remains an important nutrient that we get in everyday food we eat, because it gives us that common source of energy. So if you look at this, there's corn, there is potato, there's another type of potato, perhaps this is red potato, this could be Irish, and then this is a bowl of cereal too. If you look at, you see this beautiful which contains various sources of carbohydrate as we see in our household. Now, common other examples. Now, just these ones are the sources. The examples of carbohydrate, like I said, something that must have an aldehyde. This is the aldehyde functional group. Remember, don't forget that. This is aldehyde. And then I said it will have aldehyde or ketone, and then OH group. Now look at the OH group. You see, this is OH group, OH group. You must see a lot of OH groups in every carbohydrate molecule, or every monosaccharide or disaccharide. And again, this is the simplest of them all, the glyceraldehyde. The glyceraldehyde also has an OH group and aldehyde. Remember, this is the shortcut for aldehyde. This is the shortcut for aldehyde. So if you want to open it up, you can easily open it up as usual. So it's this CHO. That's the shortcut for aldehyde. And the same definition, there's an aldehyde and there's an OH group. So like we said, they are polyhydroxyaldehydes or ketones. Now, what are the functions of carbohydrates? Very, very important. We need to know this. Now, carbohydrates are major sources of energy. Major sources of energy, example, the glucose and fructose. Of course, glucose, most food substances are broken down to glucose. And even when they are not taken down to glucose, one way or the other in the body, the enzymes take them back to glucose, because it is glucose remains the major fuel that is broken down to release energy for metabolic activity. Now they help in the storage of energy. Now, excess glucose in the body is stored as glycogen. That is storing excess energy in human. In animals, excess glucose is stored as starch. So they form storage forms of energy. Carbohydrates also play important roles that take place in the surface of the cell, such as cell-to-cell interaction and immune recognition. And this is seen in the ABO system. Is just what gives the uniqueness to the ABO blood group system is the uniqueness of the attachment of different types of oligosaccharides or carbohydrates on those proteins, immune proteins. So those are what gives it that unique identification that make A blood group to be different from B blood group, to be different from O blood group, to be different from either the AB or just the A, or just the A alone, the AB alone. So you know the different ABO blood group system is what you get from this system. Now, they also constitute the essential structural component of several classes of organisms. Different classes of organisms contain carbohydrate as what? As components, which include the cell wall. The cell wall, some part of the cell wall is made up of carbohydrate, particularly in the bacterial cell wall is actually made up of a particular type of oligosaccharide, or you can say disaccharide rather. And then there is a skeleton of insect, like I said, the chitin, that forms the protective layer of most insects and crustaceans made from chitin, and chitin is a carbohydrate as well. And then the cell membrane, most of them are found on the cell membranes, but even in animal cell membrane, where they stay there and act as, like I said again, they here act as immune recognition bodies as well. And then they're also precursors of other biomolecules. They're also precursors of other biomolecules. Good examples are the glycoproteins, the glycolipids, and even the lipoproteins. Okay, let's not put that here for now. Yeah. So the glycolipids, the glycoproteins are all made, like you see, glyco means the carbohydrate part. Glyco means like glucose, the carbohydrate part. So they form precursors of important biomolecules in the body. And then they also form part of the informational molecule, which is what the DNA and RNA. So we can say that indirectly they also help in playing an important role in heredity, because the ribose that you find in the RNA and the deoxyribose you find in the DNA form important structural components of these informational molecules. And then we now move from there. We now classify carbohydrates. Carbohydrates are classified into 4 main classes. Some other authors might decide to lump it into 3, but for my classification and to make it more convenient, I'm going to make it into 3 classes. So we have the monosaccharide, the disaccharide, oligosaccharide, and then the polysaccharide. The monosaccharide is composed of, they are the simplest building blocks of carbohydrate, and they constitute of molecules that have up to 3 to 7 atoms to 7 carbon atoms. And good example, like I gave you earlier, glucose commonly, fructose, galactose. Galactose you get from lactose, which is milk sugar. Galactose, fructose, and glucose are common example. Now the disaccharides are made up of 2 units of monosaccharide unit. That means they're derived from the monosaccharide, but here they're made up of 2 units of monosaccharide that are held together by a bond. In fact, this bond, let me just talk about it. We're still going to do it later. This bond is called the glycosidic linkage. The glycosidic bond linkage. So when 2 monosaccharides are held together by glycosidic linkage, they form disaccharide. And good example of disaccharide is the maltose, the malt sugar. The sucrose is the commonest table sugar we eat every day. We buy the household sugar. And then even lactose. Lactose is the milk sugar. Then the oligosaccharide. The oligosaccharides are made up of, again, they are built from the monosaccharide. But in this case, they contain up to 3 to 10 monosaccharide units held together by various glycosidic linkages. And good examples here, we're going to talk about here, not much, but just know these examples. The raffinose. The raffinose and the stachose, both of these guys are oligosaccharides. And then what about the polysaccharides? The polysaccharides are the largest, and they are composed of 11 to hundreds of thousands of monosaccharide units. So a lot of monosaccharide units put together form the polysaccharide. And the common example we're going to talk about here is the starch. We're going to see the starch here, the starch, which is the animal storage of glucose. Glycogen, which is the storage of glucose, the storage of glucose in the animal glycogen. Cellulose, which plays an important role in structure and rigidity, cellulose. And even chitin that help in protecting the insect and the crustaceans. They are all examples of polysaccharides. Okay, let us immediately take it off from there. Now let's introduce stereoisomerism, because this is one of our objectives in this class. Stereoisomers also are called optical isomers because they tend to rotate plane polarized light. They are molecules that have the same, of course, every isomer will have the same molecular formula. They have the same molecular formula. Let me try to highlight those important key areas. Molecules that have the same molecular formula. They also have the same connectivity. Therefore, they are not structural isomers. What are they different? But they differ in their 3-dimensional arrangement of atoms in space around a chiral carbon atom. What is a chiral carbon atom? We're going to talk about it. Now, this type of stereoisomerism gives rise to a type of isomer we call enantiomerism. So what are enantiomers? Enantiomers are mirror images, non-superimposable isomers. They are mirror image non-superimposable isomers. In fact, these type of molecules are said to be handed or chiral. We're going to talk about that much later. They are handed. What it means is that Now, okay, let's look at this picture. This is the picture. I put this picture here. That's why I have my name there. In this picture, you can see that I was trying to place my right hand on top of my left hand, superimpose it on it, and you look at it, it's not working. That couldn't work because my hand is handed. The right hand cannot be superimposed on top of the left hand. And if you want to do that, that doesn't align. They don't align. If you look at now, my thumb protrudes here and the thumb of this one protrudes here, making sure that they can never align themselves, showing that the hand itself cannot superimpose on each other. The same thing happens to enantiomers or so many other stereoisomers. So what happens here is that the diisomers of the glyceraldehyde, this is glyceraldehyde, glyceraldehyde. The glyceraldehyde, like I have here, this is it here. Now they have the D and L form. Let's look at them. If you look at this now, you find out that these two guys now are mirror images of each other. Look at it. This is a mirror image. So this is our mirror. If this is a mirror and you put this here, this is exactly what you're going to see. So these two mirror images. Now let's look at the reference. The reference functional group is the OH group here. The OH group here is placed to the right side. That's what we say is a D isomer. Whereas the L isomer here, this is placed to the left. So this is placed to the left side. This is on the right side, making it, this is a D and this is an L. Now see what is happening here. Now, this particular carbon is unique because it contains, see this carbon contains 4 different attachments. This is 1, 2, 3, 4 attachments on this carbon. This type of carbon is said to be a chiral center or a chiral carbon. So molecules that have to exhibit stereoisomerism must have a carbon atom that has 3 different attachment or functional group on it. And that is exactly what we call a chiral carbon. And most of this chiral carbon will give rise to what? Stereoisomerism. And let us see this. So a chiral carbon, now let me now define it. I have it in my note. A chiral atom, or a chiral simply means a term used to describe compounds or objects that cannot be superimposed on their mirror images. Just like my hand I showed you. It cannot be, the right hand is a mirror image of the left hand, but they cannot be superimposed on the other. That's not possible. So then what is a chiral carbon? A chiral carbon is a carbon atom with 4 different attachments, 4 different groups attached to it. So the central atom of what? The glyceraldehyde, like I showed you, is a chiral carbon. Look at the glyceraldehyde again. This is the glyceraldehyde I showed you earlier. The central atom has 4 different groups attached to it, and therefore is what? A chiral carbon or a chiral center, if you want to call it chiral center. Now, so the presence of single chiral carbon gives rise to isomerism. A single chiral center gives rise to isomerism. And in fact, the higher the number of the chiral center, the higher the number of stereoisomers that molecule will have. And now, most monosaccharides have chiral centers. And as a result, most of them exhibit stereoisomerism. If we now go to the next thing is, so still on stereochemistry, now the stereochemistry of carbohydrate. Organic molecules can have more than 1 chiral carbon, of course, and the maximum number of stereoisomers, like I told you, the higher the number of stereoisomers, the higher the number of what? The higher the number of chiral center, rather, the higher the number of stereoisomers. So the maximum number of stereoisomers you derive it from the formula 2 raised to the power of n. What does that simply mean? What it means is that the n here is the number of chiral carbon atoms. So now if you know the number of chiral carbon atoms as n, you put it there, you now calculate the total number of stereoisomers. So a compound that has 2 chiral carbon or 2 stereocenters will be 2 raised to the power 2. So it's going to have a total of 4 stereoisomers. A compound with 3 chiral centers or 3 chiral atoms will have 2 raised to the power 3, which is equal to 8 stereoisomers. That's exactly what it means. Remember? Now let's look at this example here. This is a D-xylulose. This is glyceraldehyde. Again, this is glyceraldehyde. Now, D-xylulose here has 2 chiral centers. Let's see. Now, chiral center cannot be here because there are 2 hydrogen attached. It cannot be. A chiral center cannot happen when there is a double bond. It cannot be. Now, if you look at this guy is different from this. This is a chiral center number 1. And then, okay, let me take another color. Then this is another chiral center. Let's look at it. This is different from this, is different from this, and different from this. So there are 2 chiral centers in this molecule, right? So there are 2 chiral centers in this molecule. So if there are 2 chiral centers, the total number of isomers is going to have will be 2 raised to the power 2, and that will give you 4 stereoisomers will be possible for this particular molecule. In this one, this is the simplest monosaccharide, glyceraldehyde, just have 1 chiral center, and that's, of course, is going to be only 2 isomers. And the only isomer it's going to have will be the other enantiomers, like I showed you earlier here. The other this thing is going to be, that one I drew is going to be the D, the other one is going to be the L. So it just has just 2. All right, so this is, okay, this is the D, so the other one is going to be the L. The other one, where the OH group is facing this way, is now going to be the L, and that will be the only stereoisomers that is going to have. This will be the L. All right, so let's take the first reflection question. In the first reflection question, it says, which of the following compounds contain a chiral carbon? We're going to look at it critically. Remember, a chiral carbon must be a carbon that has 4 different groups attached to it. Let's look at the first one here. If we call this one A, if you look at it, this is the central carbon. It has this. These 2 are alike, but these 2 are different. Provided there are 2 things that are similar attached to this central carbon, that carbon is not a chiral center. So this is not a chiral. So this is not a chiral carbon. Does not contain chiral carbon. Does not contain a chiral carbon. So you can say does not have a chiral carbon. I don't have a chiral carbon in this molecule. Let me go to this one. If you look at this one now, this carbon cannot be. There are 3 hydrogens attached. This cannot be. There are 2 hydrogens attached. What about this? This may be. This, has methyl group here, has OH group, and then has another different group attached. So there are 4 different groups attached to this molecule, making it a tetrahedral stereocenter. So this carbon is a chiral carbon. This is a chiral carbon. So this molecule itself, we say this is a chiral molecule. The molecule is a chiral. Yeah. This is a chiral molecule because it's a chiral molecule because it has a chiral center. And this particular molecule can exhibit stereoisomerism. And in fact, if you want to calculate the total number of isomers, here it has only 1 stereocenter. It's going to be 2 raised to the power 1. It's going to be 2 stereoisomers. That means it's going to have only the D and L isomers. We now go to the next thing. In this question now, it says, identify and put a star at each of the chiral carbons in this molecule below, and then determine the number of stereoisomers. So we're going to look at it. If you look at this now, let's look. Now, this is the aldehyde. This carbon has C double bond O. It cannot be this one. So it can be from here. Let's count. This is number 1, 2, 3, 4, 5, and 6. 6 carbons. That's what it has. So let's look at it. Cannot be this one. It can be this one. It can be this one because this is 1, 2, 3, and a whole lot of these attached to this one. So this is a chiral center. I'm going to put a asterisk there. Now again, if you look at it now, this is another attachment. This is a different attachment. And this is attachment is different from what you have up. This is another chiral center. Then this is another chiral center if you look at it, and this is another chiral center. Now, so there are 4 chiral centers here. You can always pause this video, try to make sure you draw it individually differently and circle them and know and see that these are different. So like if I want to check this one now, if I put a very big, wait, let's see. If I put, this is an attachment, this is an attachment, this is an attachment, this is an attachment. So this is a chiral center as well. So that is how you do that. But I'm going to remove this so that it doesn't make it look tidy. Okay, so there are 4 chiral centers here, and I've put a star in each of them from carbon number 2 to carbon number 5 here. And then, so the total number of stereoisomers that it will have will be 2 raised to the power n, and where n, of course, is what? 4. Remember, our n here is equal to 4, so it's going to be 2 raised to the power 4. 2 raised to the power 4 is going to give us 16 stereoisomers for this particular molecule. Now, let's now talk about enantiomers and diastereomers. I introduced enantiomers a little bit earlier. So what are enantiomers? Enantiomers are chiral molecules that are non-superimposable on their mirror images. They are mirror images of one another, and they are not superimposable, just like the right hand and the left hand. However, what it simply means is that there is an opposite configuration in the chiral carbon in all the atoms. There is a direct opposite configuration in all. So let's look at this again. If you look at this now, this is an enantiomer of this. These two, the relation between these two is that they are enantiomers of one another. Now, the only change you have in these two is just in this configuration. This one is facing left, and this one is facing right. So there is this opposite configuration at this carbon. So in doing this, we're going to just change the configurations at the chiral carbon to get enantiomers. However, what about the diastereomers? The diastereomers are chiral molecules. They are chiral molecules that are non-superimposable non-mirror images. They are not non-mirror images. And why are they not non-mirror images? Because they have opposite configuration at some chiral centers, not in all. We're going to see an example in the next page. Some of the chiral centers are changed, but some of them are not. Therefore, they are not mirror images. And it only occurs when organic molecules possess at least more than one, at least from 2 and above. It has to be more than one chiral center for you to have a diastereomer. Now, so if you look at the relationship between these tetros, this is various tetroses because it has 4 carbons. Remember, a 4-carbon atom is a tetros. We're going to talk about this very soon. So by the time we start talking about monosaccharide, we're going to talk about the classifications. But this is the tetros because it has 1, 2, 3, 4. All these molecules have 4 carbon atoms. Now, so let's see what's happening here. Now, remember what we said? This is the D-isomer. This is D-erythros. D-erythros has the 2 OH group facing to the right. That's why it is a D-isomer. Remember, these are the 2 chiral atoms. This is chiral, the other ones are not chiral. Now, if I change the configuration from left to right to this one, I form the L-isomer of D-erythros. And the L-isomer of D-erythros is, look at it here, it becomes the L-erythros by flipping all the carbon at the what? Chiral center. However, if you want to form a diastereomer of this, what do I need to do? I can just only change one of these. So what I'm going to do, I'm going to leave this one and change one of these. I'm going to form a diastereomer. Let's see. So if you go down here now, if you look at this, remember these two are enantiomers. Now, if I go down here now and if I change the configuration of this one to form this, look up. So it used to be left here, I move it to the right. It used to be right here, I move it to the left here. And while leaving this one to the right, I form a new molecule. That new molecule becomes an erythros. And this erythros is because it is a D-erythros. It is D here because this particular carbon is still to the right. That's why we still call it a D. I'm going to tell you what this means much later. But look at it now. So the relation between these two become a diastereomer. So diastereomer simply means getting an enantiomer and flipping one of what? The stereocenter. It forms you a diastereomer. The same thing happens here. In this one, I'm going to leave. Look at what happens here now. In this one now, if you flip just this, look at what happens here now. This one used to be to the left, right? And I take it back to the right. Only at this point, I form what? The trios. And this trios, of course, is an L trios. How do we know that? Look at it. If you look at between these two, they are enantiomers of each other. Look at this. This guy is an enantiomer of this because this, look at this now, is facing this way. Look at this. The L is facing this way, but this one has been changed. And of course, so this is an enantiomer of this one. And the relationship. Then if you also look at this one, let's look at the diagonal. If you look at between this one and this one, what are you going to see? You find out that the only change they have is in one of the carbon. This is only changed in this one. This one is changed only in this one, whereas this one remains the same. Therefore, this is also a diastereomer. The same thing happens here. So for you to form an enantiomer from a diastereomer, 1, it must have more than 1 carbon, at least from 2 and above. And 2, just flip the configuration of one of the stereocenters, you now form your what? Diastereomer. And we're going to take okay, let's now talk about properties of optical molecules. So still properties of enantiomer. You see, optical activity is the property of rotating a plane polarized light. You know, when a molecule rotates a plane polarized light, we say it has an optical activity. Now, optical active molecules rotate plane polarized light either to the right or to the left. When they rotate it to the left, we say it is lavorotatory. So enantiomers that rotate plane polarized light to the left, usually designate them with minus. They are minus enantiomers because they are rotating anti-clockwise to the left. This is anti-clockwise or left. That's what you see. If you don't want to say anti-clockwise, you can say the left. So this is anti-clockwise, whereas those ones that rotate it to the right, clockwise, are said to be dextro-rotatory. So dextro-rotatory are enantiomers that rotate plane polarized light to the right. And we use plus to designate them. Now, to measure this deflection of light, either to the right or left, we use a machine called the polarimeter. The polarimeter can be much more complex. This is a sketch I made to make it a little bit simple for you guys to understand in this class. I actually drew this myself. So in plane polarized light, this is like a machine, a polarimeter. A polarimeter is composed of a light source. Like this is the light source. This is the light source, a bulb. This is a bulb, light source. And then ordinary light vibrates in every direction. Ordinary light moves in different directions, in all directions. However, in this machine, a polarimeter usually has a polarizer. A polarizer, just like you see in your sunglasses, like the polarizer sunglasses. A polarizer converts this light that is moving in every direction in a single direction. So in that single direction, it has polarized the light in one plane. So this light is moving in all planes. This is moving in all planes. And now it has been converted only in one plane, moving in one direction. And in that one direction, it is now going through a solution. This is an optically active solution or an enantiomer. As it goes through this, now look at what happens here. It's supposed to keep moving on, but it doesn't. What happens? It is now either deflected to the right for the what? For the dextro-rotatory isomer, or to the left for the lavorotatory isomer. If this thing wasn't there, the light would have continued moving straight, but that doesn't become the case. So this molecule, this particular instrument is called the polarimeter, and we use it to measure the optical activity of an enantiomer or an optically active molecule. We now go to the next thing we need to talk about. Now, like I said earlier, only one stereoisomer is found in nature. Still on those optical properties here. Only one stereoisomer is found in nature for carbohydrate and amino acid, even though they are all chiral. Now, two chiral molecules can be found in some rare cases. In rare cases, can be found in nature for some instances, but they can never be found in the same biological system. They are not. A good example is this, is that the humans can only metabolize the D isomers of the monosaccharide, the D-glucose, the D-fructose, the D-galactose, usually what the body wants. So, and the D-isomers are what you actually find in nature more abundantly. In fact, other ones that other elements you may find in nature might be artificially synthesized. The ones you may find, rather, might be artificially synthesized either in the lab or in any industry. But what you find, most D-isomers of monosaccharide are actually what occurs in nature. Now, if you come to amino acid, it becomes the opposite case. Most animals utilize only the L isomers of amino acid, only the L isomers, to synthesize proteins. And it's because L isomers of amino acid are only what you find in nature. So even nature itself has a way of dividing labor, has a way of making the divisions between these stereoisomers. Now let's take this reflection real quickly. The reflection says, circle the molecules that are chiral, identify their chiral centers with an asterisk, and determine the number of stereoisomers. Now, look at what we're going to be doing here. I'm going to start with these ones because these ones do not have chiral center. How are you going to do this problem? Let me start with them. Remember, here will be CH3. Carbon has 3 hydrogen. It can never be. If you complete this, there's 2 hydrogen here. This can never be a chiral center. The same thing happens here. And then this one cannot be because this is oxygen here. It's not a carbon. So this cannot be. What about this one? It cannot be here because this is CH3, 3 hydrogens here. There's a double bond here. It can be because double bond will only have 3 attachments. It cannot be here. Whenever you have carbon to a double bond, it can be a chiral center. What about this one? There is F and there is F, and there's a hydrogen. This cannot be a. So these ones have no chiral center. So there's nowhere to put our asterisk. We now go to this one. If you go to this one, let's count. cannot be a chiral center because this is CH3, of course. This cannot be also. And this cannot be because there is 2 hydrogens attached there. But this one can be. Let's see this carbon here. It can be because now let's see. There is a different group here, a different group, a different group, and a different group. So there are 4 attachments attached to this carbon is a chiral center. So what am I going to do? I'm going to put an asterisk at this point. And it says, determine the number of stereoisomers. It has only one chiral center. So the number of stereoisomers is going to be 2 raised to the power 1 equals to 2. And it says we should do what? Yeah, draw them. How do you draw them? We're going to draw the mirror image. Some students like putting a mirror and drawing it. That's fine. It doesn't matter. Now, let me give you the shortcut. The shortcut you need to do is that this is happening in the 3-dimensional space. That's why we use the 3D. Sorry, that's why we use the wedge, the thick wedge here, and the dash wedge. That's why we use it because of it's in the 3-dimensional. So what you need to do is to draw the skeleton first. I'm going to draw the skeleton. I'm going to give a space to myself there. If I draw this skeleton, what do I do next? Now, just change the configuration on any one of them, any 2 of the atoms, just exchange them, you get the stereoisomer. So what I'm going to do, I'm still going to use this one, leave this one here. I'm still going to leave this dash here. What I'm going to do now is that bromine used to be here. I'm going to take this bromine and put here. And then my OH is going to go over here. This becomes the stereoisomer, or in this case, the enantiomer of this one. So this is the enantiomer of this one. Let's go to this one and finish it as well. You can always pause this video, try out this yourself and come back. In going to this one, let's see what happens here. Now, again, if you look at it, there are 3 hydrogens here. It can be this one, it can be this one, it can be this one. It can only be this one. How? Let's see. There is hydrogen, there is methyl group, there is bromine, and there is this long group. 1, 2, 3. So we call this a propane group. So this is a chiral center. I'm going to put an asterisk here. And again, it has only 1 chiral center. So what it means is that the number of stereoisomers is going to be 2 raised to the power 1. Will give us only 2. And in that case, what do we do? We draw it. To draw it again, I always tell you, draw this. This is 1, 2, 3, 4. 1, 2, 3, 4. So you now put your bromine here. Now look at what you're going to do. Now you exchange this again. There are 2 ways you can do this. You can decide to change. You see, in this one, I changed the molecules. You can also change the wedge to a dash and a dash to a wedge. It will give you the same thing. If you change the dash to a wedge to a dash, it is going to give you the same thing. But I'm still going to do the same way. I like solving my problem in one pattern, not to confuse my students. So what am I going to do? Now, it's not on this one. That would have been wrong. It's on this one. So I'm going to go put this one here. And again, I'm going to do this. Now, remember, here initially has CH3. I'm going to take hydrogen and put here, and put my CH3 here. And lo and behold, this becomes the enantiomer of this one, or the stereoisomer of this one. This is how you do this particular problem. We now go to another reflection question related to that as well. Exactly the same thing. If you look at it, if you look at all this now, it cannot be anywhere here because this is the double bond here. It can be here. There are 2 hydrogens here. We can only have it at this point because this is different. There's another one here. There's another one. And the whole of this is different. So this is the stereoisomer. It has only 1. And 2 raised to the power 1 is going to give us what? 2. And if I'm going to redraw this, remember again, just change the configuration between hydrogen and this. So if I'm going to draw it, there's something that looks like a benzene ring here. Then I'm going to do this. There's this here, and there is this OH. Now the configuration is at this point. That's my interest. So what I'm going to do, there was H here initially. I'm going to take this H here and put the NH2 here. And this becomes the enantiomer or the stereoisomer of this one. Something happens here too. If you look at this one, this will be the stereoisomer at this point. If that's the stereoisomer, of course, this is different. This is different. If you look at this, is different. And again, this is also different. So here it will have 2 raised to the power 1 equal to 2. And therefore, if I'm going to draw the stereoisomer, again, make sure you put the skeleton exactly what it is. And then, yeah, I have this one here. And this one, OH. Yeah, 1, 2, 3. 1, 2, 3. I want to make sure I got everything correctly. I'm going to put my thick wedge where it is. Again, what do I do? The NH was here. I'm going to move it to NH2 here. I'm going to move my OH here. So this becomes what? The enantiomer or the stereoisomer of this one, or the mirror image, because all these ones, whenever there are two isomers, the other one must be the mirror image. Now, this is a multiple choice reflection question. It says, which type of isomer are possible in this molecule? So which type of stereoisomers are this molecule? Let's see if there are mirror images. You can draw it as mirror images, that is fine. If you look at it, they look like mirror image. This one is here, this is correct. This hydrogen is, but if you look at it, this one is to the left. No, it's to the right. This is to the right. And then this one is to the left. So this is to the left, facing it up. So this is a mirror image of this one. So there are mirror images. There are mirror images. That mirror didn't come out well. There are mirror images. And what it means is that they are what? Enantiomers. So the type of isomerism here will be enantiomers. Enantiomers. When I go to the next thing, we're getting close to the end of this class. Fischer projection. A Fischer projection was actually founded by Fischer. It depicts or shows the three-dimensional shapes of chiral molecules. So you only use it for chiral molecules. Now, but in this case, a chiral carbon is represented by an intersection. I usually tell my students it's represented by a cross. What it means is that if you have a chiral carbon here, you don't have to write a carbon. You just put a cross. Now, what it means is that the bonds written here are in two-dimensional, is a two-dimensional representation of the configuration of the tetrahedral stereocenter. Remember, the carbon is tetrahedral. Whenever you see tetrahedral, it has four attachments that are different: A, B, C, and D. Now, and then of course, it is this that you remove and represent it with. This now becomes A, B. No, does not. So if it's going to be A, B, C, and D, you now put a cross. That's what would simply mean by doing that. So the bonds that are written horizontally, the horizontal bond represent bonds that are coming in front of the paper. Represent bonds that are coming close to you that you can see. Those horizontal bonds are the ones coming close to you in front of the paper in three-dimensional space. Whereas the bonds that are written vertically are those bonds that you assume that you cannot see them. They are pointing inside or behind the paper or behind the board. You cannot see them. They are pointing away from you because we are talking about a three-dimensional molecule. Let's take some example here. In this example you have here now, you find out that in this example, you see these molecules, these have two chiral centers here. Two chiral carbons. So this is a chiral carbon, this is a chiral carbon. You see, it is so it's a shortcut. Instead of writing CHO, you put your C here, put your OH, put another C, put your OH, put your CH2. Instead of writing this carbon, you can remove this carbon and put it as an intersection between these lines. This is what we call a Fischer projection, just using an intersection to represent a chiral carbon center. It has a rule. How do you do it? Now, usually, the most oxidized carbon is usually written at the top of the projection, at the top of the structure. You write it at the top. Look at it here. This is aldehyde. The most oxidized means it can be aldehyde or the ketone. Remember, every carbohydrate every monosaccharide must have an aldehyde or a ketone. So this is an aldehyde. So you have to write it in the top and give it the lowest number possible. So if I want to number this is going to be number. I can number from here 1. It's going to be number 6. So I'm going to say 1, 2, 3, 4, 5, 6. Here again, if you number from here, this gets number 5. If you come from here, it gives number 2. So this is 1, 2, 3, 4, 5, 6. So the most oxidized carbon, whether it's aldehyde or ketone, must get the lowest number. C1 for aldehyde and C2 for ketones. That's what I show. Then other carbons can now be numbered from that sequence. Now the D configuration in a Fischer projection is that the OH group must be, this is the OH group, must be to the right of the highest numbered chiral carbon. Now what is the highest numbered chiral carbon? If you count this thing down, this is not a chiral carbon. The highest number chiral carbon here is this guy. So what it means is that for a D configuration, this must be facing to the right. So if I remove this and put it to the left, it now becomes an L configuration. The same thing happens in this one. If you count this again, if you want to count it, this is the chiral carbon. If you're counting it down, the highest number of chiral carbon becomes this again, and because this OH group is to the right, this becomes D-fructose. So this is D-glucose, this is D-fructose. Again, the L configuration, like I said, the OH group is on the left of the highest numbered chiral carbon. So the highest numbered chiral carbon is what determines whether it is a D or L isomer when you start talking about monosaccharides. Now, we're going to be taking a reflection question to cap all we've talked about here. So in this question, it says, what does it say? It says, draw the Fischer projection for the D and L forms of the amino acid alanine. So this is an alanine. Alanine is amino acid. And if you look at alanine, apart from glycine, every other amino acid has a chiral center. Let's see. This is a chiral center. This is a different in amino group, carboxylic group, hydrogen and metal. So this is a chiral center. What it means, this can be written for what? A Fischer projection. So we're going to be doing the Fischer projection for the D and for the L. What it means is that, and it says, look at the instruction. It says, base your configuration of the two D and L isomers on the amino group. So the amino group is what we're going to be placing either to the right or to the left. So look what I'm going to do first. I'm going to try to use a mirror. So this is going to be my mirror to separate the two. This is my mirror. I'm going to draw one this way. So to draw the first one, I'm going to use an intersection because that's Fischer projection means we're going to use a cross for this carbon. I'm not going to show the carbon anymore. So I'm going to say, if I draw this is an intersection to represent my carbon. If I put the amino group to the right, it's going to be NH2 here. Then I can arrange other group anywhere. It doesn't really matter. But here, I'm going to put carboxylic group here. I'm going to now put the CH3 here. I'm going to put hydrogen here. So if you look at this now, this is to the right. So I'm going to draw the opposite of this. So now, because this is to the right, this is what? My D isomer. So now I'm going to draw the L isomer. In the L isomer, remember, you cannot show the carbon in Fischer projection. You must have to use a cross. So if I use a cross again here, what's it going to be? Again, remember, I have this here, it's not going to change. I have the CH3 here, it's not going to change. I'm only going to change this one with the hydrogen. So if I move this across with the hydrogen, if I move it across, remember why I'm putting this with hydrogen is because it is the two that is here. So if I switch it with the hydrogen is now going to be here, and then the NH2 is now going to be here. And again, if you look at that, this is to the left. And because this is to the left, this becomes the L isomers. And these two are enantiomers of each other. So these are enantiomers of each other. They are enantiomers or enantiomers of each other. This is how we solve this problem. And having said that, we've come to the end of this lecture. Thank you for listening. Bye.